predicting how well a model predicts. And the idea was to try to improve this. So minimizing SSE always picks the largest model. So what I ended up doing, or we ended up doing, is I try to um, predict new data. Okay, so we try to predict new data, and in order to do that, we define this kind of prediction error. So what you do is you pick a point x, query point x star, and then you pick a um, point y star, which is mu x star plus epsilon. And this is a new fresh data point, which is independent of the training data. And what we can do is we can fit our model on the training data. We get a mu hat, and then the prediction for the response of um, this new data point would be mu hat x star, and then we compare it to the observed value. Okay, so that's the prediction error, and then we saw that if you take the expectation over both the randomness in y star, and so this is over y star and y, this would be part would be like sigma squared, which is not it's an irreducible part. This is the noise, basically the noise in the new data point, which we can't predict. This is due to that. And then there's the part which the models can improve. And that's basically how close the regression function is to the estimated regression function in the mean squared sense. So mean squared means the squared error is this. This is the squared error. And the mean here means this expectation. Okay, so you take the expectation of the difference of mu of x star and mu hat x star and squared. And so this part we can improve. And we saw, like, we argued that we could do kind of evaluate this quantity. If I evaluate this quantity over xi's and then sum them over the training x's, this gives me an interesting measure. So this would be equivalent to expectation of mu minus mu hat, where mu is just mu of x1 up to xn, and then mu hat of, oh, sorry, this is the vector. This would be mu hat of x1 up to xn. And so what we get is this criteria. Okay, so this is reasonable. This is this average is going to be, this is not for a new data point on the training data, but kind of we argued that this is going to be close to a generic, this is like the MSE of a generic data point. Okay, so what we ended up having, so this is also going to be mu s, mu hat s. And so we ended up with this risk definition, which is the critical quantity that we want to control. And this is equal to the, we ended up seeing that this is equal to the bias squared plus the variance. So this is really another way of seeing it. This is expectation of mu hat s minus mu hat s squared, so the norm squared. So this is really the bias, the difference between mu hat s and its expectation. And this is really going to be the variance, which is the expectation of the deviation of mu hat s minus the, or if you want, you can write it this way, the expectation of mu hat s minus mu hat s. So this is a notion of a variance of the estimator. This is the notion of the bias. Sorry, this is, this should be mu. So this is measuring how close the expectation of mu hat s is to the true mu. And this is deterministic quantity. This is going to be bias squared, if you want to say bias squared. Measures the lack of fit. And then there's this term, which is measuring how close mu hat s is to its expectation. We didn't do it that way, but you can do it this way. So just add and subtract. Let's say subtract mu expectation of mu hat s, and then add expectation of mu hat s. And you can expand. We did it more directly last time, but this is another way of doing it. The key is this quantity and these quantity are basically competing with each other. So the first one is going to go down when you keep adding, generally goes down when you keep adding variables. And once you have an adequate model, which means that mu belongs to the image of xs, then this bias would be 0, because in that case, hs would kill, or hs of mu would be mu. So mu is in the subspace, so it's going to be invariant when you project it. And so this is the basically residual of that projection, which is going to be 0. And so bias would be 0. So once you have enough predictors in the model such that this holds, assuming that it's possible to hold, then the model is adequate. Let's say we can say the model is adequate. And so the bias would be 0, after which if you keep adding variables, then you just increase this variance. Okay, and each variable you add is going to increase this sigma squared, like this by a sigma squared. So this is basically the number of parameters, which is the number of variables plus 1, because you have the intercept as well. And so each variable would contribute a sigma squared to the prediction error. And you can see there's going to be a trade-off. So you keep decreasing the bias and increasing the variance, and there's a sweet spot. Okay. And sometimes the sweet spot could happen even before the bias is 0. So this is something that we kind of all are going to maybe see later. If you care about the prediction, you don't necessarily need to have a 0 bias. You just want to minimize this. And the minimum could happen even if you have a non-zero bias. Okay, so far so good. Remember this. So this is the key kind of criteria. There are several issues with it. Like what is the main issue with this? Okay, if I have this, then why do we continue the discussion? I can use this to score the models and find the model that minimizes it. What's wrong with it? Yes, so there are two things that are missing. There's the sigma squared, which is easy to fix, and there's the mu. So sigma squared, we usually estimate and replace here by usually the estimate from the most, the largest model. So let's say the model that picks everything. So let's call this, or like the S max, which contains all the covariates. So I fit a model like this, and I get a sigma hat squared S max, let's say. I can plug that in. So I include all the covariates so that I know, let's say, the bias potentially is 0, hopefully. And so I get it. I get that. This one is more challenging. I think last time Jude was in the office hours, and he asked the question, so why can't we just also estimate the mu and then plug it in? And so we try to do that. So one thing that you can do, which is, I mean, the first thing that comes to mind is just estimate it by mu at S. So we fit the model, you get a mu hat S. I can replace with mu hat S. And this is not going to work. You can immediately see that I minus HS is going to kill mu hat S. So you get 0 bias. So the model is not going to have 0 bias, but because you fit, it's like the issue that you fit the model using the same variables, it's going to predict that bias is 0. The next step is, so this is not going to be good because we only see the variance. We know that bias is necessarily not 0 for any subset. So it doesn't work. The next step is like, can I do mu hat S max? So similar to the variance, I fit the largest model, I get a mu hat S max, and then I plug that in. And then interesting things happen. So this is not an obviously bad measure. So what you can do, and what we did in the office hours, like you could do a bit of calculation. You plug it in, and then you calculate the expectation. So let's say R mu hat S max. You compute the expectation, and you see that the expectation has some extra terms. So it's going to have like a term related to the bias, but it has extra terms, and you try to correct for those terms. So do the computation, and then try to correct it. You get an unbiased estimator. So you can come up with actually a criteria that involves this by adjusting it properly. Similar thing that we did last time with the CP, and I'm going to go over that again. So it's doable. It turns out that the variance is going to be high. So you can, I mean, all these criteria that we talk about are about like the expectation. So you come up with a kind of like a criteria whose expectation is the true risk. So you might end up like minus something or plus something would have, you can correct it to have the correct unexpected, on average, or expectation is uh, R mu of S. So this would be an unbiased estimator of the risk, and so we can use it, but it could have a variance which is higher than the variance of the criteria that we discuss. So the variance we don't talk about, but it's very good for you to try to reason, okay? So is the idea clear? So you fit the largest model, you get an estimate of mu hat, you plug it in, and then you try to compute the expectation of this. Things like HS max come in. So this, for example, would be HS, or HS max minus HS. This is a projection operator because the models are nested. So you can use these properties that we have seen before to simplify. And then you would get an expression for the expectation of this, which we can correct. So it was a very interesting discussion. If you're interested, you can go do that and then implement it and see what happens in practice. Okay. And in particular, I would encourage you to look at the variance. So do it many times, plot it, and see how the variance behaves. Okay, anyways, so this is the criteria that we have, the Oracle criteria. This we call bias. Really, it's a bias squared, but we call this bias. So it's like BS plus sigma squared DS. If I have this, I get an Oracle method which outputs the minimum. So subset of variables that minimizes this. That doesn't often, I mean, we don't have the Oracle. So last time we tried to start from the SSE, and then we calculate the expectation. It turned out that it has the bias, the correct bias, plus this extra term. Okay, so that extra term comes out of the calculation, and you can see the problem here. There's this negative sign here. So if I add variables, ds is going to increase, so negative ds is going to decrease. So both this term and the first term are going to decrease. This we also see. So from the regression, we know that it decreases exactly. This is saying on average, it also decreases. Like statistically, it's also, both of them are decreasing. So that's the problem. So what we did is you can just subtract this term and add back sigma squared ds. So that would remove this, right? And then I get this plus the term that I want. So if I add it to the other side as well, so subtract and add, I get a criteria which is likely. So this is saying that the expectation would be equal to that, or really the expectation, once you simplify, you get the expectation of the SSE minus sigma squared n plus 2 sigma squared ds. This is equal to bs plus sigma squared ds, which is really r mu of s. Okay, so this criteria is also unbiased. So that's the criteria that people usually work with. So you start from the SSE, you look at the expectation, you correct for the wrong variance, basically, term, and you get this twice the ds. So what you do is like you argument, this is a good criteria, SSE, s minus sigma squared n plus 2 sigma squared ds. So if I minimize over s, this is going to give me a model selection criteria. Sounds good? Something we did last time. Any questions? So once you realize this, there are different ways of basically writing this criteria. The argument is not going to change if I, for example, divide by sigma squared, okay? So if I divide everything by sigma squared, nothing changes. Why is that? So you're looking at it as a function of s. And so if I multiply like divide by sigma squared, I'm dividing all, like, as a function of s for every s, we had a value, now it's divided by sigma squared s. So the location of the minimum is not going to change. Okay, so this argument is saying what subset minimizes this? The subset that minimizes this is the same as the subset that minimizes the above. Okay, another thing I can do, for example, is I can drop a constant, also equal to SSE, s plus 2 sigma 2 ds. Okay, it's also equivalent to this because this term is constant. The argument doesn't change if I divide, like drop it. It's also equal to argmin over s. I can now, for example, divide that criteria by n. So I get SSE, s divided by n, plus 2 sigma squared ds over n. Okay, that criteria is also the same. So all these 4 criteria give you the same model selection criteria because you're either dividing by a constant or removing a constant. And when you locate the location of the minimum as a function of s, it doesn't change. Okay. So this one, if I estimate it by sigma squared, so replace sigma squared with s squared or slash or sigma hat squared if you want, this gives me the malloc CP. So malloc CP would be SSE of s divided by s squared or sigma hat squared if you want. Let's do s squared. This is from the largest model of it, minus n plus 2 ds. Okay. And you can try to minimize this. The version where, let's call this version C tilde P, this is based on the actual variance. So we know that the expectation of this guy, the expectation of this, we know that the expectation of the top is this, that we divided by sigma squared, so the expectation of this is really that. Okay. So one thing to notice is, for example, R mu s is like BS plus, so if I plug in what this is, I get ds divided by sigma squared plus 2 ds. Sorry, plus ds. Okay. So what happens is that for the models that are unbiased, so if the model is adequate, if model is adequate, then expectation of CP tilde would be ds. Okay, so for adequate models, the bias would go away. This would be ds. And this is the criteria that people really, I'll show you a picture. When you plot, or traditionally people plotted all these values for all the subsets, and all the adequate ones would be as a function of the number of parameters, and all the adequate models are close to ds. So CP would be close to ds if you have, so if you have like 5 parameters in your model, and you calculate the CP is very close to 5, then the model is adequate. If you have 7 variables in the model and you calculate it as close to 7, it's adequate. If you calculate it as like 15, then it means that there's this term present, so it's biased. So it's like, doesn't have enough parameters. Yes?
Yeah. Square M.
Oh, here?
Yeah.
So in which step did we get rid of it? So here, I mean, from this line to, I mean, from this to that, is that? Or this?
No, not the one on.
Right, in this one.
Yeah.
Okay, how do we get rid of the sigma squared n? Anyone wants to?
We divide by sigma squared and we.
Yeah, so these are like basically independent steps. So from this to that, and this is like you can go directly from this. You don't have to go, like I can go directly from this step to this one. How do I do? Yeah.
Just because minimizing, we're minimizing s, so even having the constant there doesn't change.
Yes, so the key is that this is the argument, right? So suppose you have a function, like I have like something like this, right? if I shift it up or shift it down, the location of the minimum doesn't change, right? So imagine this is a function of S. I mean, it's not possible to write it as a function of S because S is like a subset, but this applies to a general function. So if I shift it up and down, the location of the minimum is not going to change. The other thing that we did is like, for example, multiply by a number. It's like going to change the shape, but it doesn't change the location of the minimum. Okay. Does that answer your question? Yeah, okay. Any more questions? Yes.
For your application of p total.
Yes. I did not drop the constant. You mean this one, right? I actually didn't. So if you look at this, this is the exact thing whose expectation is R mu S, right? When I divide both sides by sigma squared, the CP tilde is really this, what I define it is here, right? Yes. So if you drop some of these, then you're correct. Then this argument that this is equal to ds is not. So I was careful not to do that. Yeah, thank you. So if you don't care about the value, if you just want to minimize it, it doesn't matter. For the CP, I could have dropped this. It's okay, but people care about the value traditionally. It doesn't matter as much, but the way that defined it, this is really an unbiased estimator of the prediction risk divided by sigma squared. And so this has this nice feature that when this is 0, you know the value. So you know for adequate models, it has to be equal to the number of parameters on average. First, it's on average. Second, it's for the one that we know the variance. So the actual thing that we have in practice is this. It's going to fluctuate, as we'll see. And also not exactly because of the variance is not going to be exactly sigma squared. It's going to be slightly biased, but it's fine. Does this make sense? So this is basically the general approach, right? So we have a criteria. We try to find an unbiased estimator of it. It's like a prediction risk or fixed design risk, I call it, I think, in the notes. Hopefully I'll share. But it's a measure of prediction performance, and we try to come up with an unbiased estimator. Here is one. And then we try to minimize it. The other thing, any questions? The other thing what we discuss is it gives you the same thing. As I mentioned in the morning lecture, all roads lead to Rome. Okay, so there's this criteria that comes up in different formats. This format, for example, is the one that you get if you argue via that optimism theorem. Okay, so what was the optimism theorem? The idea was that if you look at the training data, or the training error, this is really the SSE divided by n. And it's going to come down, and it keeps going down as you add more variables. But the test error, which is like an estimate of the actual prediction error, this is going to go up, and this gap is the optimism. So this is the optimism of the training. So your training would be more optimistic about your prediction risk or prediction error. And if you can try to estimate it, I can add it back to the training, and I get the test error. So yeah, there are ways like cross-validation we talked about that tries to estimate this test error directly by resampling. What we're doing here is trying to come up with a criteria, unbiased criteria, that directly estimate this without any sample splitting. Okay, CP is 1, AIC and BIC we'll see. The other criteria is actually equivalent to CP more or less. This was via the optimism. So you have this training error, which is really the SSE divided by n. And then we define this in-sample prediction error, which is what you would get if you replace the yi with an independent copy at the exact xi. So this yi prime really is a draw from mu of xi. You use the same xi, but you draw from the model again, so the noise is going to be independent. So this epsilon prime is independent of all the training noises, hence independent of all the y's in the training. And so you look at this, the so-called in-sample prediction error. The in-sample is because the xi's are the same as the training. And I believe, I didn't show it, but you're welcome to try to show that this is really, again, the risk, the actual risk that we did above divided by n. So you're basically comparing the SSE divided by n to r mu s divided by n, which we already did on the slide that I mentioned. But this is via a result of Efron, which is very nice. That tells you the expectation of the difference of these two guys. If you write it in this way, it's easy to compute the expectation of the difference. The difference is called the optimism. So the expectation of the difference turns out to be this quantity. And this is true. I encourage you to try to prove it. So you just expand. When you take the expectation, look at the expectation of this. If I take the expectation of this, I get expectation here. So you just expand this and then subtract. And some cancellations happen and you get this. And for this result, you don't need any linearity. So there's no need to, what you only need is y is equal to mu plus epsilon. Something like this. The mu hat here is really y hat. So mu hat and y hat are the same. I'm using the mu hat I notation most of the time, but people use y hat I as well. So the y hat I here in our case, or mu hat, is in regression, it's linear, is a linear function of y, but need not be the case. So this result is more general. It holds for nonlinear estimators as well. So any way that you combine y's, you can combine all the training data, you can fit a neural network, you get a mu hat. And this result still holds. Okay, yes?
Multiple vectors or xis that are associated with a single observation. So basically,
so that's the idea. So actually, so xi's here are xi's are fixed here, but all the observations are gone into predicting yi. That's like mu hat I is going to be h. Let's say for regression, it's going to be h yi. So you're going to use all your observations. So all the x's and all the y's are used in predicting yi. That's exactly the case. It happens that this is still equal to what I wrote. Okay, that's the theorem.
how to select yi given that you have multiple predictor?
I'm not selecting. So this result, I'm not selecting anything. I'm saying that this is equal to this, despite the fact that all the y's and all the x's have been used in predicting each data point. Okay, it still turns out to be true. It's not an obvious thing, just you have to write it down. It's an interesting fact, and it's fairly general. It's saying that basically the average correlation of y hat I and yi is the difference between the training and the covariance is twice that is the difference between the training and the test on average. Okay, that's all it says. Okay. It's not trivial. You just have to write it down. It's a very interesting result. For linear models, so this in the linear case, linear model, we know that this is going to be like the trace, 2 over n trace of covariance of mu hat and y. This is really the trace of that. And then we calculated this last time, and it turns out to be sigma squared ds. So this turns out to be 2 over n sigma squared ds. And so if I add it back to, so the training error is this. This is too optimistic. If I add the difference, the optimism, I correct it by the optimism. So optimism corrected training would be that. If I do argument, this is the same criteria that we had before. Okay, one of the incarnation of that same criteria. Okay, if you go back to this is really the optimism, expected optimism. Okay, you can either derive this criteria just directly from expectation of SSE, or from this more general result, which holds for any estimator, linear or nonlinear. But in the linear case, it's going to turn out to be that. And then I mentioned that because in this case, in the regression, if I divide this quantity covariance of y hat I and yi divided by sigma squared, that looks like a degree of freedom, exactly the number of parameters. This is used as a definition of degrees of freedom. So you define the degrees of freedom of a general. So if you have a general nonlinear function of y, let's say, that's predicting mu hat, you can define its degrees of freedom as 1 over sigma squared covariance of y hat I and yi. And it turns out to be, under the Gaussian error, it turns out to be actually equal to this. This we didn't prove. This is easy to prove. This requires the Stein's lemma. This is saying this is the expectation of the divergence of that function, basically. And these are in regression. Again, we have seen this is like how sensitive y hat I is relative to yi is really hii. So this gets back you the expectation of the trace of h. I mean, there's no expectation here in our case. It would be just trace of h, which is going to give me ds. So the degrees of freedom is really ds for the. But this one is minor. It's not minor, but we're not going to worry about this. But if you're interested, there's this. This is the definition, and this comes from the Stein's lemma. I'm going to post some notes if you're interested. You can. This is only under the Gaussian model. So if you have y is mu, basically normal mu, variance sigma squared I, then if you have an estimator gy, then you can calculate the degrees of freedom by taking the partial derivatives of this. This is like partial derivatives of, let's call this y hat I. Partial derivatives of this function with respect to y. Anyways, so this is a side. The whole point is the optimism theorem allows you to do optimism corrected SSE training, and this gives you the same criteria, same as CP with known variance. Okay. Again, this has the unknown variance here. So far, so good. This is basically what we did mostly last time, except for the Stein's lemma, which I'm not going to spend time on it. If you're interested, you're welcome to look at. Questions? So new stuff is this AIC, which is, so as I mentioned in the earlier course, I mean, this is enough, but statisticians had to do something for the next 50 years. So they came up with more stuff, so a lot more stuff. So you have like there are many other criteria. So one is like the AIC. This is like he's, I think, I can't pronounce his name or spell his name. Information criteria. And so this is just generalizes this idea of trying to do optimism correction, or like correcting for the optimism of the training to a more general model. So you have a likelihood, a general model, it has a likelihood, for example, in like if you have the yi, in the linear model it would be normal x. Let's say beta would be theta here in this case. I'm going to do theta sigma squared I. And so you have the likelihood, if you remember, we did a little bit of that. Likelihood would be just you write down the PDF, and just view it as a function of parameters. So it would be negative 1 y minus x theta squared divided by 2 sigma squared. So that's the likelihood, and then I can minimize or maximize the likelihood, or I can take the log. That would be the log likelihood, and I can maximize the log likelihood. That would give me a parameter estimate. Okay, so here, okay, let me write it as theta. So the parameter could be either theta is just beta, or in the non-variance case, non sigma squared, or theta is beta and sigma squared in the unknown sigma squared case. So you can either take beta as the parameter, assuming that you know sigma squared, or you can take both of the beta and sigma squared and maximize over both. Or equivalently, you can minimize. So if I do theta hat min, it's equivalent to arg min. Let's say negative, I can put a 2, it doesn't matter here, but it appears in the criteria. So negative 2 log likelihood, I can now minimize it. It's equivalent to maximizing the log likelihood. So this behaves like a loss function. Okay, I minimize it, and then I evaluate the log likelihood at, or this loss at theta hat m. This is like our fit. This is like the SSE. So like the SSES in regression. So this measures how well you fit. and it's going to be optimistic. And then AKK's idea is like you correct it by the 2 times the number of free parameters in the model. Okay, if theta is restricted, if it's not restricted, then it would be the number of basically elements of theta. But there are some asymptotic information theoretic ideas here that like he argued why this should be that. And if you do it for Gaussian regression, let's say if sigma squared is known, you can easily calculate the beta would be just beta hat would be just the OLS. And you plug it in, you would get just the SSE divided by sigma squared plus some constants. The constants come from when you take the log of this part. It will be a constant because sigma squared is known. And this part you can see is just going to be negative. Once I take the log and multiply by -2, this go away, and then you get the SSE divided by sigma squared. Okay, so this really is going to be SSE divided by sigma squared plus some constant. So when I do the IKK like criteria, I just have SSE. This is from the first this part, and then I add twice the number of parameters, which would be ds. So this gives you the same criteria that we had before. Okay, so same as CP with known sigma squared up to the constant. So the constants are different, but we know that the constants don't matter. The thing is that if sigma squared is unknown, things are a little bit more interesting. You can estimate the sigma squared as well. Anyone remembers what would be the MLE of sigma squared in this model? I shouldn't talk all by myself, though we don't have so much time. Anyone remembers? So if you do maximum likelihood, what happens if I have both of them as parameters? It turns out that the beta hat would be still the OLS. But what about the sigma hat part? I briefly mentioned it. Yes. Bias version, yeah. So it would be just 1 over n, like you would look at the residuals divided by n rather than n-1. Okay, like minor difference, but that would be the MLE. And you plug both in now, and things would simplify because there's no longer would be the sigma squared would not be a parameter. So plug everything in, and you get this criteria. So the first half, this part would be just n log SSE divided by n. You can see it's like, again, a monotone function of SSE. It's not exactly SSE divided by n, but it's like a monotone, plus some constant, and then you'd add the 2s. In this case, the criteria, this is the AIC that people might use for regression. The advantage is that it doesn't have the unknown sigma squared that you have to estimate. So you just automatically estimate it from MLE. You plug it in, but it has the same flavor. So this is lack of fit, and this is the complexity penalty. So it penalizes the large models. Okay, it's similar to this, but this part is like replaced in a way. Sounds good? Okay, that's the AIC for you. But again, the statisticians were, they had too much time on their hands, so they came up with BIC. Unfortunately, there's no CIC or DIC or so BIC is Bayesian information criteria, right? Bayesian info criteria. So Mr. Schwartz in 1978 proposed this via an argument, a Bayesian argument. So you put a prior on the parameter, and then you have a posterior, and then you try to approximate the posterior. It turns out that once you do that, you get the same criteria, except that you get this log n here instead of 2. So 2 in AIC. This 2 we have seen a lot coming up. In all the criteria that we did, all this manipulation, you can see the 2 comes in. So all of these have a 2 here. This wasn't by accident. If you go through the argument, you see this comes up, either through the optimism or... So AKK has the same thing. So Schwartz, like, criteria replaces this 2 in AIC with log n. So again, this is not ad hoc. It came up from an approximation. If you're interested, you can check it out. So if you do this in the unknown sigma squared case, you get this part would be the same, and you just get log NDS plus constant. So that's going to be the BIC. So the only difference is that this term is now penalizing the large models more heavily. Okay, if you have a large model, let's say if n is bigger than 8, rather than 2 times ds, you pay log n times ds, which is growing. And so this tends to push things towards smaller model. Okay, tends to select the smaller models. And there is this result that, let's say, if there is a true subset S star among the candidates, the design is identifiable. There's a bunch of other things like omitting the true signal increases the expected SSE by order n, or asymptotically. There's a criteria here, like the minimal signal strength. But under these, the BIC would be consistent in the sense that the probability that S hat BIC is equal to S goes to 1. So if there's a true model and a bunch of other sort of assumptions hold, then BIC selects the correct model. Whereas AIC is not going to select the correct model, and so by proxy, the CP and stuff, they're close to AIC. They're not going to select the correct model. So in other words, a BIC is model selection consistent. Okay. What AIC does, so in this fixed truth regime, they're generally not support consistent. They tend to pick a slightly bigger model. What they're going to penalize severely is the underfit. So underfit models are rejected, but if you overfit a little bit, they're going to be okay. Not too much, but generally you're going to have a slightly bigger model. So why do we care about AIC or all the other ones? They really came up from the risk prediction. So what happens, what the property that they have is the prediction loss is kind of efficiently preserved. So asymptotically, the risk of the subset that the AIC, or let's say CP, selects is approaching the risk of the best subset. Okay. So in terms of the risk, you pick the one that predicts best. The BIC doesn't have this property, but BIC selects the true model. Okay. But this is a little more general because if there is no true model, let's say the model, there's no linear model, this still can hold. So you approach asymptotically the best subset that predicts, but there's no kind of notion of consistency, model selection consistency. Okay, that's kind of the very rough picture of the difference between AIC and the CP and the other criteria mentioned in this BIC. Okay, BIC is, for this reason, people like statisticians really like it, but this requires a lot of assumptions. So you have a true model, it's linear, there's a true subset, the true subset is kind of identifiable. You don't have this issue that identifiable means like the columns of X are like, it's like the linearly independent and they remain linearly independent in the limit. And so you need some sort of assumptions there. Then it would be model selection consistent. Any questions about this? This little slide is like summary of like some theoretical understanding, which we don't go into. I'm going to post like a chapter, hopefully, like has some argument if you're interested. Why this is true, for example. It's a little bit beyond the scope of this course. Questions? Okay. Let me show you some. So I mean, yeah. So that's the caveat. It's not like that AIC is not consistent but better, and BIC is not worse for prediction universally. So they target different goals, and under certain conditions, what I said holds. But there are a lot of cases in which they behave similarly. Okay, the models are similar. So this is an example. So we have 5 true covariates in the model. I simulated it. Say, for example, you have like x1, x3, x5, x10, I don't know, x11. Okay, out of we have 25, a pool of 25 predictors. This goes all the way to 25. And I have these, and I kind of select them in a particular order. Let's say I pick x1 first, and then x1, x3, and then x1, x3, x5. And all the 5 first, and then I add one wrong predictor or noise predictor. And then you can see all the criteria sharply drop. So these are the ones that are not adequate. So they don't have enough predictors to span subspace that contains mu. But once you have all the 5, they kind of basically have a minimum, and then they start to go up, and you can see the BIC sharply penalizes. So it goes faster than everyone else because of that log n. This is the AIC, mallows, this is the AIC. They're very close here. But you can see they're kind of flat. So it's easy if there's a bit of variation to pick a mallow with 6 predictors rather than 5. And then this is the cross-validation that we'll talk about a little bit. Okay, so this is an idealized simulation path. So for example, here, I'm just looking at a single model with 10 variables, but there are really 2 to the 10 possible subsets. Here it's going to be 2 to the 25, which is really 2 to the 5 times 2 to the 10 to the 2. This is roughly 10, like 1,000 to the 2. This is like 1,000,000. This is like 32. So at this point, there are 32 million models. So if you want to score them all, you're welcome to do it, but it's not really in practice feasible. This is called all subset selection. So we set argmin over S a certain criteria, let's say AIC S. So we can write it, but in practice, it's not possible to minimize over all subsets because there might be too many subsets. So if you have 100, 2 to the 100, it's not going to be feasible, okay? It would be 1,000 to the power 10, okay? So well, people like this all subset selection would work, we'll see, like in a small number of covariates, you can score all of them. There's another issue with this. If you have too many, once you start selecting, like trying to do them, the variance of these these criteria will creep in. So if you score many things, by chance, one of them could be too small, one of them could be too large. So we said the expectation is okay, but once you do a lot of them, then you have to worry about the variance of this. So by chance, you could the fluctuations would come in. So there are statistical issues and there are also computational issues. This is a more feasible approach. This is called forward stepwise regression. To trace a path, I pick, let's say, the first covariate, which is the most correlated with the response. Okay, I'm going to go over the pool and look at each covariate and pick the one that's most correlated with Y. That would be the model with a single covariate. That's my candidate model with a single covariate. Okay, that would be this. And then I form the residual and then see what is the most correlated predictor among the pool, the remaining pool, with this residual. And then I add it to the model. That would be my model with the 2 covariates and so on. Okay. So at each step, you compute the residual and look at the most correlated residual to the remaining predictors. Okay. That allows you to trace a path through this jungle of model selection like models, and you can see this does similar. So it goes down to around 5, and then the behavior is qualitatively, in this case, similar. So this is called forward stepwise regression. You just have to fit 25 models at most. You don't have to score 2 to the 5 models. But it's greedy. It could go wrong. So you could kind of it's not necessarily guaranteed to pick the best model. Okay, if you're lucky, the first 5 are the right one. But if you make a mistake, that's going to stick in the model, and you might end up having to add more covariates to compensate for the wrong one. Okay, and then this is the difference. The same plot, I'm doing it in the greedy path, and you can see similar behavior happens here. Okay, so let's look at this plot. This is the traditional CP plot. This is what traditionally, if you look at the book, it also has this. So 2 to the 8 here, we have 256 subsets total. This is manageable. So I have 8 covariates. Q is 8. So we do all subsets regression. So you score all these models, okay? And so, for example, you can see at 5, I have 2 to the 5, 35 models, okay? And I'm actually not showing, I'm showing all of them. But potentially for each one, you get a dot here. So this is one model, this is one model. And you just, at this point, for example, all the models here have 5 parameters, including the intercept. So they have 4 predictors. And the ones that are here, what are these guys? What do they have going on for them versus these guys? So these one all have CP close to DS. The ones that are close, this is the 45-degree line. So the models that are close to this, CP is close to DS, which means they're adequate. Yes. So they have the right covariates in them. The ones that are up there, they don't have the right covariates. They're paying a huge price because of the bias. Okay. So this line kind of, this picture kind of separates them into clearly two camps. So we don't care about these ones because they're underfitting. So these are underfitting. And among these, all of them are adequate, but you're going to pick the one that has the smallest one. And you can see the CP is like growing, okay? So there's no need to include like 8 covariates if a model with 4 covariates is adequate. You can see there's nothing here at 3. There's no 2 predictor model that is adequate. And so we have to go to 3 predictors. There's one model here I'm going to pick. And I'm not going to pick. Okay, so potentially if you minimize explicitly, you might actually pick this one. There's one here that has maybe slightly lower CP. This is due to the fluctuation. It's possible that you pick that, but traditionally people just plot this and then pick the first one that is near the line. Okay, this allows you to like, avoid the fluctuations as well. But if you just go by minimizing CP, you might pick this, which is fine. I mean, you just have like one extra covariate in your model. Okay, that's the CP plot. Does it make sense? To go back to that plot and see why this makes sense. So that's why we kept the form of the CP so that for the models that are adequate, not underfitting, they're going to be all close to this line. Good? All good? Okay, so let's see what we have more. Okay, so all of these were like penalty methods, or we try to basically find an unbiased estimator of the risk. And the thing that they have in common is that they don't need sample splitting. So you train on the same data, you use the same information, use all your samples, but they have a lot of assumptions baked into them, with various degrees of generality. So cross-validation is more general. So you directly estimate the test error or that risk by splitting your sample. So you split your sample. This is very common if you have done any sort of machine learning into like a training set and a test set. And then you train on this part and you score, you basically get a mu hat function, and then you apply it to these guys. Let's say I'm going to apply it to mu hat. Let's call this x star I minus y star I. That would be my estimate of the prediction error. Okay, so you can try to predict the test set, and you get an estimate of the prediction error. And because of the independence, this is going to be an unbiased estimator of the prediction error, okay? Empirical estimator. And then you can score based on that. Okay. This is very common in machine learning, especially a single split. You do a single random split, let's say 80%, 20%, or 60%, 40%. The statisticians would do a slightly different approach. They would, for example, do a k-fold cross-validation, which is you split it into k. Let's say k is equal to 3 into 3 equal sized pieces. And every time you train on k minus 1 of them, and then you test on this. So this would be train, and this would be test. Next time you do train on these two pieces and test on the middle, and this next time you do train on this part. Oh, sorry, did that one already. So we train on this part and then test on the other piece. So this has the advantage that every data point participates in training and test once at least, okay? And then there are different ways of dealing with this. So you can like compute the test errors, the average of the test errors, and then average them again, or you could do something maybe a little better. You just do compute the average of these prediction errors where you compare the yi to the prediction on the fold in which it wasn't participating in the training. Okay, so this guy, for example, is only in this fold, it's in the test, in all other folds in the training. So I'm going to use when I'm gonna like measure this yi of this, I'm gonna compare it with the prediction on this fold. On this fold, it was in the test, so it didn't participate in the training. So this is gonna be independent in a sense from that. And for each data point, it's gonna be in one of the folds. And so for everyone in this, it's going to be comparing on this fold and so on. So you can form this once. So you basically form the average yi minus y hat I, where minus ki means like on the fold in which the I wasn't present. Okay, and if you do k equal to n, you can see like if you do n-fold cross-validation, this is exactly leave one out case. So you're comparing, for example, this data point is out, we're training on this, and you're comparing this would be like yi, the way I wrote it last time, or a couple of lectures ago. So you leave that out, you predict based on the rest, or train based on the rest, and try to predict this. Okay, so there's the special case where k is equal to n. Every point is its own test set, and so you have n of these, and so that would be leave one out cross-validation. Is the idea clear? And usually you do like k equal 3 or 5 or usually 10. I mean, these are possible. There's a bit of mention of, so a smaller k means you're gonna fit, so if k, for example, is 2, you're training on half the data, okay, not the full data set. So your sample size, effective sample size is smaller, so you're a little bit more pessimistic about the performance. Okay, so your actual model is going to have more data, so it's going to be better. So it's going to be a little bit more pessimistic. Oftentimes, once you do this, you train on everything. Once you want to like ship your model, you figure out, for example, use cross-validation to set up pick the model, all the parameters. That we can also do hyperparameter tuning, for example, if you have extra parameters in the model. For us, we just have the subset. We want to pick the subset, but later we'll have methods that have hyperparameters, and you can select which hyperparameter should I choose. Choose it based on minimizing the error here. And so it would be a little bit pessimistic if k is very large. This statement is not quite correct because you can do k equal m and it's going to be fine. But generally speaking, there's going to be more variation in a sense. So if you let's not worry about it. This is not exactly, we have to check it. But the choosing k is not obvious. It's not an obvious, there's no obvious trade-off. It's a little bit tricky. So not quite correct. So ignore this. So this is the workhorse in machine learning. So if you did any machine learning, that's what you do to try to score. And that's why machine learning succeeded so much. So people split your data, try to predict, and then they compete and try to improve the prediction. And over like 10 years, like you're here. So let's say you can predict, like you like talk to your machine. That's because this is like a very nice way to try to assess the model performance, predictive performance of the model. And then you can tune all the hyperparameters that you have. You can compare the models. It avoids explicit likelihood or degree of freedom calculation. You don't have to calculate any degrees of freedom. You don't have to assume Gaussianity. You don't have to assume it's anything, basically. You just directly estimate by sampling or resampling the prediction error. So in regression, as we've seen, the leave one out has a very simple. So these leave one out residuals have this form. And so if I compute the cross-validation criteria for the leave one out, I get this nice form, which is called the sum is called the press. So it's going to be press residual divided by n. So in linear models, you don't actually have to do this split. If you do like n-fold cross-validation or leave one out cross-validation, you have the actual thing all at once. Okay, it's just normalize the residuals by these 1 minus the leverage scores, square them, and then average them, and that gives you the leave one out cross-validation. There's another thing called the generalized cross-validation, which you replace the HII with the average. So the average is, if you remember, this is the sum divided by the average, divided by n, and this turns out to be actually like ds in our case plus dou over n. So this would be just a fixed thing. But if you replace it with the average, you get this criteria, which is called generalized cross-validation. Let's say in our case, this is going to be HS. Later, when we talk about ridge has a different edge here, and it has like a tuning parameter lambda. So for regression, it doesn't really make sense like OLS because we can do this exact thing. But if you do it like this, then you can extend it. So if I replace that, so the leverage points we have seen, like the leverage scores could be very non-uniform, especially if you have outliers. But if you just take the average and replace it there, once I do that, this comes out. So if I do EI divided by 1 minus trace of H divided by N, then this is a constant comes out. I get 1 over N summation EI squared divided by 1 minus trace of H over N squared. And this is really the SSE. So you get the SSE divided by N, and then this thing is kind of trying to adjust for the optimism in a sense. This is proposed in the context of ridge or other like smoothing splines. I'll talk a little bit about this next time. But this is another criteria. You can try to select based on this. For the OLS, it doesn't make much sense, but a little more general result. This has the advantage that you don't have to resample again. Okay, so this has the property for linear smoothers. If you have a matrix here, this makes some sense. We'll see it like in the next lecture. Okay, one last thing I want to talk a little bit about is any questions? So this concludes like the model selection criteria. So we have the penalty methods. The majority, a lot of them like are equivalent to each other in this like known sigma squared case, CP and AIC, and did the optimism correction. And in the when you don't know sigma squared, AIC is a little bit different, but behaves similarly to the other ones. The BIC is the one that's very different, and it penalizes the models that are more complex, more severely, and it's model selection consistent under certain criteria, whereas the other ones are not model selection consistent in general, but they are asymptotically efficient predictors. Like they select a model that whose prediction error is the best in a sense. So this one, any questions? And then okay, we talked about the cross-validation, which is like a resampling approach to estimate the prediction error. So far, mostly we talked about prediction error, except for the BIC, which can handle model selection. The thing that I wanted to mention is this very important piece, which is select then test is a trap. So far we have been selecting models. So you have a very nice procedure, let's say now to select. You select your subsets, you have a regression now, your regression model, you fit your regression, and then you have this nice machinery of F-tests and T-tests and confidence intervals, and you go about trying to apply those, and that will be all wrong. Okay, so you're gonna have, none of the things that we discussed would hold. So they are not gonna be valid confidence intervals or valid tests after you select your model. And the easiest way to see is do this experiment for yourself. You'll see why. So you have y, let's say, is just pure noise, 0 plus epsilon. So there's this, the model part is 0. You just have epsilon. And then you have, let's say, go pick some predictors, x1 up to, let's say, xp. These are, let's say, independent. So they're the normal 0i, let's say, and they're independent of y. So the predictors are completely independent. Y is also, let's say, epsilon is also, could be known sigma squared I. So everything is noise. So you have a bunch of noise vectors, okay? And then you try to like regress y on these. Technically, nothing should happen. So you should come up with 0. So there's no relation between y and x. But let's say I want to pick the best one predictor model. Okay, I'm going to go and look at all of these coordinates, or like the predictors, pick the one that's mostly correlated with y. Okay, pick xi that is most correlated with y. Okay, let's say this happens to be xi star, and then I'm gonna fit a regression. So fit a regression or regress. regress y on xi star, you get kind of like a beta hat 0 and beta hat 1. Let's say it's just, this is going to be just a simple linear regression. And then I want to test, for example, whether beta 1 is 0 or not. Okay. And we are under the null, so there's nothing there. So it should come out that the beta 1 is 0. So I shouldn't be able to reject the null. If you go there, and then from this, you can compute your test. T is t-test, for example. Or build the confidence interval, or actually you can compute the p-value. Let's say I compute the p-value. You get your t statistic, you compute this p-value, and then repeat the experiment. Repeat this experiment many times, you get a distribution for the p-value, and this is the distribution that you get. Okay, you're under the null, but your p-value, which should be uniform, is basically has a distribution that's very much shifted towards 0. So it's as if you're under the alternative. So what happens is that most often you're going to reject the null. You think there's something there, but there's nothing. Okay, so what happens is you picked a covariate that's most correlated, and then you try to see, is it really correlated with y? And you confirm that yes, it is very correlated. And you'll be very happy, and you publish your paper, and no one can reproduce your result. This happens a lot, okay? So any sort of selection that you do, you're gonna select one that's highly correlated. By your procedure, you're selecting something that's highly correlated. Even if it's noise, it's gonna have some correlation in the end. And then you try to test whether it's correlated, whether beta 1 is 0 or not, and oftentimes you reject. Okay, so this is sometimes called double dipping, and it's not obvious to people, and it's very good for you to try this and try to see what happens and then convince yourself. So your test would be completely wrong because you're going to be rejecting. If you reject at level alpha, you're going to reject a lot more than 5% of the time. Okay, this is 5%. So it's not going to be 5% of the time. You're going to reject, let's say, I don't know, 50% of the time. So your test would be completely uncalibrated. Is that kind of, does that make sense? Just maybe just ask you, is there a solution? Can you find a solution? Maybe I'm a little bit out of time, but how do you fix this? Yes.
Train set, a validation set, and the test set.
It's close, but here you just have to split. Yes, you don't need three. I'll talk about that maybe later. But yes, data splitting is a solution. So you split your data, let's say into two pieces at least. Okay, you're gonna do your selection here, right? And if your selection requires a piece, right? So then that's the validation part. So let's say I split into two parts. I'm gonna select the model on this based on this information. Then I'm gonna fit on this and do my test here. Then this, because they're independent, this is not gonna happen. So, and in this case, when I'm trying to do the cross-validation, I might use some of these criteria. It doesn't need any splitting like the CP, or I might try to do cross-validation, then you do a little bit of split here. That would be the validation part, right? Depends on how you want to do model selection here. You may or may not need the validation, but this split matters if you want to do tests. So you have to separately select on one piece and then test on the other piece. This is called data splitting, and it's one solution. There are other solutions that people, this is a very active area of research called selective inference. If you're interested, you can check. That's all I'm going to say about it. Okay, thank you guys. We'll come back next time, talk about ridge and lasso and stuff.